Log on, tune in, find out. Another good idea from Cambridge.
So our next speaker is Mark Sapir, who will speak about Hilbert compression of groups and dimension growth.
Okay, thank you for inviting me. It's nice being Cambridge. I'm going to talk about group theory, so it's a group theory. The thing is that in trying to solve some problems, So trying to solve some problems in group theory, we actually came to some combinatorial questions which are very easy to formulate, and nobody so far. So and it's a basic combinatorial question which I want to give you today. So that's the thing. So the main concept. In fact, let me start with the group. So the group I'm going to talk about just one particular group. It's called Richard-Thompson group. It's a famous group. It's just one group, and so there's the canonical definition. There are several definitions of that group. I will give two. So the canonical definition is that it consists of all like increasing piecewise linear maps from 0, 1 to 0, 1. So it's a homeomorphisms from 0, 1 to 0, 1, increasing, and it's a piecewise linear. So the graph looks like this, and all breakpoints occur at dyadic numbers, so it's like a over 2 to the power n, and all slopes are powers of 2. Okay, so that's a definition of Thompson group. It turns out that this group is actually 2 generated. It is also has 2 relations, 2 defining relations, and it has many other properties. One property of this group is that it doesn't contain concatenations. Yeah, and one property which was noticed right at the beginning when the group was introduced in the 60s is that this group doesn't contain free subgroups. And in fact, it has the following property. So if you have a subgroup of this group, any subgroup, and it is not abelian, then it contains free abelian subgroup of infinite rank. So if you have this group which is called F, and you have some subgroup G inside F, which is not abelian, then it contains a large abelian subgroup. And I mean, the abelian subgroups of this group are not something mysterious. They're very easy to understand what they are. So if you take, say, 2 functions, one function takes some. So this is your interval from 0 to 1, and one function takes some subinterval into itself and is identity everywhere else, and another function is like that, which is to take some disjoint interval to itself and is in identity everywhere else. So these 2 things commute, and of course you can put this infinitely many intervals, disjoint intervals, and you get infinitely generated free abelian subgroup, right? And there are lots of such things. Right. So, and again, so if you have a subgroup which is not abelian, it contains infinitely generated abelian subgroup. So it cannot have a free non-cyclic subgroups inside the F. Moreover, you can actually have. I mean, we proved with Victor Guba that we can go further. So if G is not solvable of class 2, then it contains Z ris Z. It has a ris product of 2 Z's inside. Now this is what? It's a semi-direct product of infinite power of Z, and Z acts on it by just shifting. right? Shifting factors. Okay. Moreover, you can replace solvable of class 2 by solvable of class n, and then here replace by so z. So if g is not solvable of class n, then it contains an iterated product of n z's. Right. So there is some lots of complicated subgroups, and in fact, how to get the risk product of two z's inside f. You can also do it very easily. So let's take again the interval. You take a subinterval. You take some function which is takes the subinterval into itself, right? And take another function. So this is here called f, and another function which takes this interval into some disjoint interval and act anyhow on the other part of the interval, right? Then, so this is called g. Then f and g generate z ris z. In fact, if you don't know what z ris z is, this is it. So that's what z is, right? So that's a group, okay? And again, so as I told you, that f contains lots of such things. And in fact, what you can do next, you can take this group and take a copy of this group on a very small interval. You can always take your interval, your group, and shrink everything, right, to the subinterval, right? And then you take another like g1, which takes this interval to outside. So what you get is that f, g, and g1 will generate z, ris, z, z, ris, z, and so on. So you can do that anytime you want. And in fact, you can take a union of all that, shrink it again, and do another z with another z. So what you can get as a result, you can have a very large subgroup of f, which is again 2 generated. In fact, it will be 2 generated, and it will contain all possible iterated risk products of C. And it is what is important. This group, let's call it B. It was first noticed by Matt Breen. This group is what is called amenable. Now, amenability is the main object of this talk. So let me introduce it. What it is. So we call a subset of a group. So if you have a group G, we have some number n, and we take a subset, finite subset x. We say that x is Fellner, 1 of n Fellner, if you take the boundary of x in the Cayley graph. So there's a Cayley graph of G. G is finitely generated, and x is a subset of the Cayley graph. You view it as a set of vertices. The boundary is the number of, all the vertices which are connected to the set but outside the set. If you take boundary, divide by the number of elements of x, and this is smaller than 1 over n. That's 1n Fellner. And the group is called amenable if for every n there is a Fellner subset. For example, Z is amenable, right? So Z, the Cayley graph of Z is just a line. If you take subset from minus n to n, the boundary consists of 2 points, right? So this point and this point is a boundary. So the quotient is 2 over 2n plus 1. So this is a Fellner set, 1 over n Fellner set. Okay, so the main question is whether F, the Thompson group, is amenable. That's a main question which nobody knows how to deal, and nobody even expects the answer, and nobody knows what the answer is. The most kind of, so why is it interesting? It's because, again, so this group doesn't contain free subgroups. So if it was amenable, so if it was non-amenable, then it would be counterexample, in fact, finitely presented counterexample to von Neumann conjecture, and it's kind of easy counterexample to von Neumann conjecture. So that's kind of justification of why is it interesting. But in fact, the real justification is that there is no idea how to do. It's just, you can also justify anyhow you want, but yeah, there is the dichotomy conjecture whether the group is amenable if and only if it contains free subgroups. So it's known that it's not true, but for finitely represented groups, it's also known to be not true now by Arshansky and myself. But our example with Arshansky has like about 10 to the power 10 generators and similar number of relations. This has 2 generators and 2 relations. But again, this is just a justification. But real thing is that there is, I mean, group theory cannot deal with such results, such groups for some reason. And one of the results which show that this problem is complicated. So the problem again is that F is amenable or not. So can we find Fellner sets for every n or not? And the statement which is justifies why is it, I mean, tells why is it complicated. It's just recent result of Justin Moore, which say that if F is amenable and X is 1, like 2 to the power n Fellner, then, sorry, X is the Fellner set, then the number of elements in X is at least 2 to the power 2 log n times. So it's more than a Tower exponent, and in fact much more than a Tower exponent. So I mean, there is a conjecture of Gromov which say that this group is amenable, but we will never know because it is not provable in piano arithmetic. And that's I mean, this kind of functions you cannot construct in piano. That's like arithmetic. But anyway, so we don't know if it is amenable. We know that it's very hard to prove. Okay, so that's a result, and that's and the problem. There is another property which is weaker than amenability, but it turned out that for Thompson group it is as hard to prove, and it's a property A. It's a Gualian U property A, and I don't even, I mean, it's kind of a version of amenability. It's just you want not one Fellner set, but Fellner sets containing every point in some sense, and it's not quite you take the boundary over X, but something similar to that. And I think Gulnara is going to talk about that property tomorrow or in 2 days on Wednesday. So okay, I'll let her introduce it. But that's another property which is similar to amenability and is weaker, certainly weaker, because so for example, free group satisfies this property, and every hyperbolic group satisfies this property. And in fact, it's very hard to construct a group which does not satisfy this property. But we don't know if Thompson group satisfies it. And okay, so okay, and there is another property which implies property A. That's called the finite asymptotic dimension. These are all properties of the same kind. They are properties of the Kelly graph, and they are very similar. In fact, there is a recent work of Didak which shows that all of these properties, like finite dimension, property A, amenability, they can be formulated in the same language in a very similar way. Okay, so finite asymptotic dimension is the following thing. We say that a space or a Kelly graph of a group has dimension n, asymptotic dimension n, if the following thing happens. If we can write down X as a union of n plus 1 families of finite or of bounded subsets, so finite subsets. In fact, UI is a family, right? So it's a family of UIJs, where every UIJ is bounded. So it means the diameter in the Cayley graph again, UIJ is smaller than some constant C, right? So that's the first property. And then the main property is that the distance between UIJ and UIK, distance between any two subsets in one family, should be bigger than any number lambda given in advance. Again, you pick a number lambda, you want n plus 1 families of finite subsets, right, which cover your X, such that each set is uniformly bounded. Each set in each family is uniformly bounded, and the distance between any two subsets in one family should be bigger than lambda. For example, the standard example of find the asymptotic dimension. This notion was introduced by Gromov, and so it's a similar to covering dimension, except it's a coarse version of that. Okay, so for example, on a plane, so plane has dimension 2, right? So we need to find 3 families of subsets, and this is how you do it. It's usually when I give talks in some room with brick walls, that's how it is done, right? So 1, 2, 3, 1, what is it? Whatever, 3, 1, and so on, right? So you just no way. So there is okay. So you color these bricks like by color 1. This is color 2, color 3, and it's clear. Okay, so the distance between any two ones is as you want. It depends on the size of the brick, right? And you need 3 families, right? So the dimension of a plane is 2. Okay, the dimension of a line is 1. Okay, so that's nice. So that's another. So this property implies property A. I think it was proved by Gvalian, but is it? So he can Hickson and row. Okay. So but anyway, so it is true. This property does imply property A. It doesn't imply amenability because free group has dimension 1. It's a tree, has dimension 1. Okay? So that's another property that we are going to talk about. And in order to give you, and the fourth property, I guess it's embeddability into Hilbert space, coarse embeddability in fact, you can replace Hilbert by any Banach space, and it's also interesting property, and I'm going to talk about it a little bit later. So if you have say a metric space X, for example, again Cayley graph of a group, and you have a Hilbert space, we are interested in a function which may distort distances, but it distorts distances in a controlled way. So the distance between the image of two things. So first of all, you can assume that it is smaller than the distance between x and y times c, so it's like Lipschitz map, and it is bigger than some function rho, which is called the control of embeddability, control of the distortion between a function of distance between x and y. So it means that this, for example, it means that if you take two distinct points, yeah, I didn't say, of course, rho is increasing function, and it goes to infinity. So for example, if you want quasi-isometric embedding, you must have a linear function here. That's a quasi-isometric embedding, but in general, quasi-isometry usually is not enough. For example, you cannot embed, say, a tree quasi-isometrically, but you can embed it almost quasi-isometrically with function very close to linear, arbitrarily close to linear. I mean binary tree. Okay, so what was noticed by Günther and Kamenker is that if we have an embedding of a group, so Günther and Kamenker noticed that if we have embedding of a group into Hilbert space and such that this thing is bigger in the asymptotic way, bigger than square root of the distance. So if rho is bigger than square root, then the group satisfies property A. Now, if we can embed it in an equivariant way, equivariant means that, so we have now talking about a group, and a group acts on a Hilbert space, and we embed our group as an orbit. So we pick an group now, if we have a situation that group acts on the Hilbert space, and we have some element h from here, and we embed g into g times h. So that's an embedding. So it's kind of particular kind of embedding. If we can embed this way, and again rho is bigger than square root, then the group is amenable. Group is amenable. Okay. So the question is, what happens to Thompson groups? Again, we don't know if it is amenable or it has property A. How does it embed into Hilbert space? So, so first of all, it is not very difficult. I mean, you have to know some kind of theory of Thompson group, but it's not very difficult to construct an embedding, and it is done in our paper with Arjantseva and Guba. It is not very difficult to construct an embedding, in fact even an equivariant embedding of f into Hilbert space with rho precisely equal to square root of it. Okay, so then maybe we can do a little bit more, and the answer is no. So we cannot, I mean, again, we cannot get n to the power alpha where alpha is anything bigger than 1/2. There is no such embedding with alpha greater than 1/2. Why? Let me explain you why. So for this I need another definition of Thompson group, and the definition is the following. It's more combinatorial. So let's consider transistors. So a transistor is a box with wires going in and going out, right? So that's a transistor. Now we start with one basic transistor. Two wires go in, one wire goes out. Okay, so that's a basic transistor. Now what can we do with transistors, or in general? So if you have two transistors, we can add them together. That's the first operation. It is just a transistor obtained by putting one next to each other, next to another. That's a new transistor. It has now 6 in and 7 out. Right? So that's another transistor. That's the first operation. Second operation which we can do with transistors is, another thing also, you have to take a transistor without a box. So that's of course important to have. And another operation is if you have one transistor which has m output wires and another transistor which has m input wires, we can multiply them, just glue them together. So these wires, so and we have another transistor, right? So that's a new operation. It's multiplication. So it's addition, it's multiplication. The third operation is flip or inversion. You just flip it along about horizontal line, right? So that's another operation. And one more thing which we need to do is if we ever have situation like this, say if you have a transistor followed by the same thing but flipped, we can replace such a picture by just two wires. Or if we have one transistor like this followed by the same transistor which flipped, it's the same, it's equivalent to just one wire. Okay, so now what? Now we take okay, so now for example, no. For example, you have to know what's inside.
They have a personality.
Yeah. So the transistors is everything which you can get using these operations from this thing and this thing. Right? So that's all transistors you can get. For example, if you take, for example, you can do 2 goes to 1 and add a trivial one, right? And then you put like this transistor and another one, and here, like this is one. This is a picture, right? It's one of the examples of a transistor that you can get, right? So you take the basic one, add one trivial, and put things on the top to make it. Now we have a transistor which is one input and one output. Right?
How do you get different number of inputs and outputs from this four?
Sorry?
How do you get a different number of inputs and outputs from these operations, from the four operations?
That's a different, right? It's 2 in, 1 out.
Yeah, but how? But you said that you get everything from a line and it's four basic operations. How is it four?
No, not from the line. With 2 to 1.
No, line and this one.
So
there are two basic things. So this is just empty, and this is 2 to 1, right? You can get anything any number of inputs and any number of outputs. Okay, so now the thing is that if you take all possible transistors with one in and one out, what you get is a group. You can, it's easy to see that multiplication is under this multiplication and under this equivalence relation. So it's easy to see that this thing is identity element, right? This thing is identity element, and what else? So the inverse is just a flip because of these things. Taking inverse is just a flip, and the product is associative. It's kind of obvious. Okay, so and this group is exactly Thompson group. So the Thompson group is obtained from this basic transistor using this operation, and so you can also have you don't need 1 1. You can take say 2 2. You get the same group. So what you get is really you get a category with objects like natural numbers. Morphisms are transistors, and the Thompson groups are local groups of this category, if you wish. So, but it doesn't really matter. So this is a Thompson group. Okay. So okay. Now it happens that this is one of the generators of the Thompson group. I told you that it has 2 generators. This is one of them. Another one is obtained from it's the same thing. So you take 2 trivial transistors and 1 non-trivial, and then you put the same thing or something like that. right? And you just continue until you get one more. Right, so that's the second generator. So Thompson group is generated by these two things. Okay, good. So now,
Can you tell us the relations? The relations?
relations are they're not complicated, but they don't say anything. It's a commutativity of some word with some other word. It doesn't really say
How
much.
long are they? How many letters in the relation?
Let's see, something like 7 or 8. Not very short relations. Something like, so if this is x0 and this x1, so x1 to the power x0 squared commutes with x1, I think. It's one relation and another one is similar. Okay, so this is a definition of a Thompson group, and from this definition we can construct subgroups. For example, we can construct a billion subgroups in the Thompson group. By the way, of course, the interesting thing is that, okay, so we have these generators, so we have the word length, or the length in the calligraph between any two elements, right? So it's the shortest word representing an element. Now, there is another natural length, or a natural norm in this group. It's just the number of basic transistors inside. Now, these two lengths are equivalent. It turns out it's very important for this theory is that in order to count the word length or count the number of transistors, it's the same up to a factor of 6. So one is bigger than another times 6. Okay? So now how to construct a billion subgroups? In there. Okay, so let's take any element in this group and put a trivial element next to it, right? And then another one, do the similar thing and put a trivial element to the right of it. These two elements commute. The product is just right, whatever, it doesn't matter what the direction is, right? It's a similar thing as for functions. If you have two functions with independent support, they commute. That's the same thing. Okay, they commute. Now, this element is not in the Thompson group. It has 2 and 2, but we can make it in Thompson group by just conjugating with the basic transistor. Now these two elements are in Thompson group and they commute. So we found z squared in the Thompson group, right? So these two elements, they commute, generate z squared. We can do more. By the way, so how many transistors does it have? It has whatever, so I don't know. So how many transistors does it? I mean, maybe like 6. I don't, just for simplicity, let's put it 6 here. So it's like 6 plus 1 plus 1, 8. And this is also 6 plus 1 plus 1, 8. So now, suppose that we found 2 to the power n pairwise commuting elements of norm n. Suppose that we found them. Okay? So we put them together. So they commute. And so on. Okay? Right? So they commute, and now we double this picture. So we take, so we first put trivial thing onto the left, right? We have 2 to the power n such things, and then put trivial thing to the right. Trivial transistor to the right. So we have another 2 to the power n transistors again, and now we have 2 to the power 2 to the power n plus 1 things, right, which pairwise commute, right? Of course, they are not again in the Thomson group, but we can conjugate. We add 2 transistors, right? In each of them, right? And now we have 2 to the power n plus 1 pairwise commuting elements of what norm? We added 2 elements, right? So the number of elements, of pairwise commuting elements, is multiplied by 2, but the norm is increased by 2, right? So it's, okay, maybe it's a Cn and it's a Cn plus 2. Okay, so what do we get? We get a copy inside z to the power inside f. It contains a copy of z to the power 2 to the power n, and the generators go to elements of linear norm. So this embedding is not only quasi-isometric, it's much more than that. So it is quasi-isometric with very little, so it's very large dimension, right? But the lengths of the elements are very short. It's linear lengths, okay? So now, suppose that our Thomson group F embeds into Hilbert space. Then, of course, all these abelian subgroups also embed there, right? In particular, of course, this abelian subgroup contains a ball or cube. The metric here is L1. So the balls are cubes, the 2 to the power n dimensional cube, right? And we embed it into H, into Hilbert space, right? So then, of course, there is standard thing in the Euclidean geometry. If you embed a cube, then the sum of this, if you take a cube or whatever, take an image of a cube in a Hilbert space, then the sum of squares of diagonals is smaller than the sum of squares of edges. That's a kind of the baby version of Poincare inequalities here, okay? And so how do we proceed? So what are the lengths? So now we have this thing, that's z to the power n. It has a cube inside, right? The diagonals, the lengths of diagonals, yeah, so again, so the length of every edge in this cube is the length of the generator, right? So it's n. The dimension is 2 to the power n, so that the length of the diagonal is, okay, so let's denote d to be 2 to the power n. The length of the diagonal is the dimension times, it's an L1 length, times the length of the edge. The length of the edge is log d. So the length of the diagonal in the cube is d times log d. And if you take this inequality, we immediately get that at least one of the diagonals, if you take just the sum of the diagonals and take the sum of the images, so this distance, at least one of the diagonals which has an original distance like this, turns out into distance square root of d log d. So the distance, if you take it, so there exist 2 points which form a diagonal of the cube, right? So the original distance between these 2 points in the cube is this, and the distance in the Hilbert space is that. So that means that the compression, the compression function, this rho, for every embedding is rho of n is smaller than square root of n log n. So what does it mean? So first of all, as I told you, we cannot have embedding with n to the power alpha where alpha is greater than 1/2. There is no way. The second thing is we cannot lose the hope here because of this square root of n, square root of log n. Right? We cannot get rid of square root of log n. That's the thing. So and this is true for every proof related to amenability of Thompson group. It fails, but it fails barely. Right? So there is a hope that we can get an embedding with compression something like n log n or something. In fact, I suspect that we can get an embedding with a compression which is inverse function of the function produced by Moore. Remember Moore's function, it was 2 to the power 2 to the power log n times. We take inverse of that function, and that's going to be the thing which we put here. But again, it's only conjecture. It's one of the things which we don't know. So again, so this fails. This approach, the GroupNet, yeah.
So, but you know that F doesn't contain undistorted copies of z to the k arbitrary.
It is undistorted.
Well, no,
it is quite asymmetric.
I mean, completely undistorted.
It certainly does not. It cannot contain. No.
You can prove that.
Yes. It's no finite engineering group contains such a thing.
Okay.
So the images of z to the power n must be at least logarithmic. It's because the number of words of say constant length is constant. You cannot. So it must be logarithmic. So this is the smallest possible embedding of z to the power n into any finitely generated group, and it happens here. Okay, so we don't know. So what happens really, and does it imply property A or amenability? We don't know. So that's the first thing. The second thing which happened, we started working on it with Sasha Dranishnikov this summer. And originally, it was not related to any Hilbert spaces or embeddings into Hilbert spaces, but it turned out to be very related. Okay, so it is easy to see that, let's talk about asymptotic dimension. It's easy to see that asymptotic dimension of z to the power k is k. I told you z to the power square, z to the 2 has dimension 2. It's easy to see that this cube has dimension 3. Z to the power k has dimension k. So in particular, and of course, z to the power infinity has dimension infinity. So f has asymptotic dimension infinity, right? So then we should stop and forget about asymptotic dimension altogether. But it's not quite what we want to do. Let's fix a lambda. And and find again f to be a union of i's, so I from 1 to n depends on lambda. And ui is we also again assume that it's collection of uniformly bounded subsets. So which means that usually we refer to this as colors. So we color f in n of lambda plus 1 colors, so that each color is a union of blobs which are uniformly bounded, and the distance between uij and uik is again greater than lambda. Okay, so now let's lambda depend on n. Right? It must depend on n. We know that we don't have a constant function lambda. So what is this function? Let's take the minimum lambda, this function, lambda of n. Okay, so the question is, what is it? So, and Dranishnikov, let me put his name, proved that if you have a group with polynomial function like that, so not only just constant but polynomial function, then it satisfies property A. Okay, so polynomial property A. Okay, so what is the question is, okay, so what is this function? This function is interesting from group theory point of view because it is it's a quasi-isometry invariant, and all such functions are interesting in geometric group theory. But for us, for example, this is a nice property, polynomial. This function is called dimension growth. Now, this function, for every finitely generated group, this function is at most exponential.
N of lambda or lambda of n?
N of lambda, yes, of course. Sorry. N of lambda. Right. This function is at most exponential. Why? If you take just a finitely generated group and we connect 2 points at distance lambda, right? We get a graph, which is called the Rips complex. So we connect 2 points at distance lambda, and we have a new graph, right? So what is the degree of this graph? It's exponential in lambda, right? So the degree is exponential. We can color this graph in the degree +1 colors. Right, so we can say that each uij is just 1 point. 1 point, and we need 2 to the power, exponential number of colors. So that's is at most exponential. So the statement we proved with Dranishnikov is that dimension growth of the Thompson group is exactly exponential. Is exactly exponential. Okay, so we found the group with exactly exponential function. It is and still embeddable into Hilbert space. So what is interesting? So then we try to say, okay, so what happens for the amenable subgroups? So I told you that Thompson group contains large amenable subgroups. For example, contains B, or it contains like series Z. It contains all the iterated products, Z, and so on. It contains group B, right, which is amenable. So all these groups are amenable. So what happens to that? And it turns out that we can prove that for these groups, say B, so we only can prove the lower bound square root of lambda. Exponential of square root of lambda. We cannot prove exponentiality of so the question is, we cannot prove. It doesn't mean that it's not true, but we tried, and several other people also tried. And so the question is it true that if you have amenable group, then this function is always strictly sub-exponential? We don't know. That would be a kind of property which distinguishes Thompson group from amenable groups. And the question is actually, it boils down again to the question about z to the power n and the coloring of our ordinary grid in z to the power n. So the question is, what is lambda dimension of z to the power n? Again, lambda dimension is the n of lambda. Right? It's a bad notation. Z to the power k. So for z to the power k, and let's take, okay, so lambda is some strange thing. It can be arbitrary number. Let's take number 4. So we want to color infinitely many colors z to the power k, such that every color is a union of uniformly bounded blobs, and these blobs are a distance at least 4 from each other. Blobs of the same color, a distance at least 4 from each other. So the question is, does it depend on k? So is it smaller than a constant? So what we know is that it is, okay, so let's see. We know that n of 4, right? N of 4 and k of 4, right? So it's a dimension, it's a 4 dimension of z to the power k, right? It's 4 means the distance between any two blobs of the same color must be at least 4. So we know that it is greater than k for k smaller than 16. That's it. So in fact, if you take lambda here and we take 2 to the power lambda, then that's what we get. But what happens for k greater than 2 to the power lambda? We don't know. It may actually stabilize. We don't know. So the conjecture is that it grows, but grows slowly. So nk of lambda is something like maybe log k, asymptotically. We don't know. That's a basic question about z to the power k. So you want to color z to the power k. So how complicated can that be? So you have a solution. Okay, so that's I mean this fact is not trivial. The fact that here you need to count the number of integer points in some polytopes and
So now,
things
now
like
we have
that.
to be concrete. Distance is just L2 distance. Distance is
L1 distance.
L1.
L1 distance, which is equivalent to L2, but then you need to
Yeah,
slightly
now
change.
we are
It's L1 distance.
very concrete.
Right. So that's a concrete question. So if this thing indeed grows slowly than k, then we can prove that at least for this group, it is, I mean, this is greater than, so it is exactly equal, exponential square root of it. If it grows slowly than k, we know that nk of lambda is always smaller than k plus 1. But again, how slowly it does it grow, we don't know. This is clearly a kind of basic combinatorial question about coloring z to the power k. And of course, the proof again uses the same group, the same abelian group. The same abelian group. I mean, again, so we have this result for z to the power k. So for if k is smaller than 2 to the power lambda, then it is equal to k. And then using the fact that we have z to the power k very lightly distorted inside f, we prove the exponential bound here and exponential to the power of square root of lambda in B. Okay, so that's basically the thing I wanted to tell you. So this is so I want you to say. So this is, for example, another interesting thing which was related, but it turned out to be simpler. So what is, say, 3 dimensions of z infinity? It's a nice exercise. So again, it was open problem for some time, like about 2 months. And then it was solved, now it is exercise. It was solved by Dmitry Panin from London, and then also Justin Moore solved it different way. But okay, so the answer is it's infinity. So you cannot color z to the power infinity infinitely many colors, so that the distance between any two blobs is at least 3. For 2, it is equal to 2, because I mean that's easy to see. But 3 dimensions, so n of 3 is infinity for z to the power infinity. But again, we are interested in finite dimensional spaces, z to the power n, and that's a question which I wanted to ask. So what is the 4 dimension of z to the power k? Is it constant, or is it the opposite think is it equal to k plus 1?
So if you take big boxes, then somehow the uncovered part is very small fraction, right, of z to the k. Just
Yes.
okay. And then you would hope that if you shift them randomly,
What will happen to the things which are not covered yet?
You mean that the construction has to be somehow like tiling, repeating
yeah,
itself?
so I would want to take some tiling with then,
Maybe, I don't know. So, I mean, many people tried this. I mean, and I don't know I don't know anybody in combinatorics who tried, but like topologists tried this, and like people in dimension theory tried. This is a dimension theory, right? People in dimension theory tried, and I tried. It didn't work. Okay, so that's it. Thank you.
Any more questions?
I've got a group theory question. Your subgroup B of the Thompson group,
Right.
it's not soluble, is that right?
It is not solvable.
It is amenable,
It's elementary amenable.
elementary amenable.
Right.
So is there an example of the subgroup of the Thompson group which is known to be amenable but not elementary amenable?
No. No, there is no. The thing is that for Thompson group, there is a conjecture that if you take a non-elementary amenable subgroup of Thompson group, it contains a copy of Thompson group. Thompson group contains lots of copies of itself. Actually, I almost told you how to prove it. And the thing is that it may, like every subgroup which is not elementary amenable might contain a copy.
Mark, do we know so we don't know the dimension growth function for the
We know it's exponential. Did I? Yeah, here.
Oh, that's okay.
Okay. There is another thing which I forgot to mention, and maybe I should mention it now, but there is another kind of spaces, where this argument will not work, namely expanders. So for expanders, what's the dimension growth? So expanders don't embed into Hilbert spaces, but so the conjecture is that expanders have exponential dimension growth. Again, we don't know how to prove it. So the only proofs are based on this z to the power n, and expanders may have dimension 2, so just ordinary dimension 2s. But this exponential dimension growth may be, this exponential growth may be exponential. The dimension growth may be exponential for expanders, at least for some expanders. So the conjecture is that if you have, for example, group with sub-exponential dimension growth, it must act non-trivially on a Banach space which is uniformly quasi-convex. Uniformly convex Banach space. It's like a result of Goyan view that every hyperbolic group acts on uniformly convex Banach space. So maybe it may not act in Hilbert space, but it acts on uniformly convex Banach. It could be that if you have sub-exponential dimension growth, then it also acts.
I think I'm missing something with the definition. So about this growth of n of lambda, we fix in your question for zk, you fix k.
Yes.
And you want to know how it will grow as a function of lambda. That's
going to be a constant, k plus 1.
So this is obviously a constant.
Yes. Not so. What I'm interested here is when it depends on. So we fix lambda,
So you fix
but
lambda and you get k.
yes. So now k is changed. So for example, lambda is equal to 4 or 3, and I want to find this number depending on k. And the question is it constant or not?
Any more questions? So let's thank Mark again.